My name is Magnus Hjorth, and I'm one of the technical lead engineers on this project from the front grade side. So I'm going to have a 15-minute presentation here about this device. So it will be quite kind of high level, but I'll try cover some interesting details about it. So yeah, starting with an introduction. So what is this exactly? So it's a processor component targeting the space industry, which we are developing. And we are doing it on ST Microelectronics 28 nanometer FD-SOI platform, and with their space GOP2 libraries and such on top. And from our perspective, it will be the successor to the GR740 as our high-end processor product that we will sell as a component to the industry. And this development is funded via several European Space Agency programs as listed here, and the Swedish National Space Agency, as well as by front grade internal funding. So just the kind of high level features spec sheet kind of slide. I'll cover some of this later. This is a block diagram which has been shown in a few earlier presentations today. It's quite busy. There's a processor system with caches and memory controllers, and then there's a whole bunch of peripherals around it. One thing I could mention a little specially is our DDR controller, which I work quite a lot with myself, which has a very strong EDAC. In the strongest mode, it has a 96-bit wide interface, and it can correct basically two 8-bit wide devices that are giving incorrect data. For example, a Ceph on one device and a random SCU on another device. And there are some Ceph recovery strategies built in. If we do a high-level raw numbers comparison with our current 740 product, which was made on 65 nanometer, we can see that there's more than a 10x increase in every dimension, like CPU instructions per second, RAM capacity, bandwidth, I/O bandwidth, etc. This is thanks to moving to the more advanced node, of course, and also moving to more modern interfaces for memory and I/O based on SerDes and so on. So, I mean, if you look at it as an upgrade, it's a major leap up. A little bit about the processor system. So we have 8 RISC-V cores in there, our Knoll 5 core, of course, which is our high-end IP core, with dual issue in order pipeline, and a variety of the extensions, like virtualization extensions and compressed instructions and hypervisor and a whole list. And yeah, and there's a core mark score around 5.02 which I just got a few days ago with a new version of GCC that improved things a little bit. And we're doing something which some people think are a little strange in this device, but we are including actually both our Leon 5 and our Knoll 5 processor inside, and we have a switch between them. So you can use the chip in RISC-V mode with the 8 Knoll 5 cores, or you can use it in Spark mode with the 8 Leon 5 modes, and you basically select with a pin. And I mean, the reason we're doing that is that we have an existing ecosystem, and we have customers that an existing user base that may want to keep using Spark for a while at least, but then we want to tap in, of course, to all the developments that are happening in RISC-V and the ecosystem. And yeah, so we provide both, and there was a question earlier on implementation and so on. So there are 2 pipelines inside basically, and they are muxed. And we share the cache memories and most of the other things around it. An interesting technical detail is that the two architectures have different NDNS, so a lot of NDNSs switch in the system, which I think people who have worked with hardware implementation can find kind of amusing. And that's also one of the reasons why they call Leon and Noel, because if you switch NDNS, the bytes change order there, so Noel is Leon backwards. So you can look at it as we provide a transition path for people who want to move from Spark to RISC-V. So I mean, you could build the same, let's say, application board, and with just a resistor option, for example, the same flight board could be used in a mission where you want Spark software, and then you could use the exact same hardware in a mission where you have RISC-V software. So I mean, it creates a lot of flexibility. And I mean, another reason we're doing it is that it is expensive and a big endeavor to make a component. So I mean, making two would, it would be hard from that perspective. Another aspect of the architecture I thought I would highlight a little bit is that we have a banked or striped interconnect, which means that basically we have a separate memory hierarchy through L2 cache down to the memory controller for different internal banks of the memory. And we can map these in different ways to memory addresses. So by default, we just spread the memory space evenly across these stripes. And by chance, most of the times you have a L1 cache miss, they will end up on different stripes. But you can also configure it to be more explicit. So you have certain CPUs that always go into one bank. And that way you can build a system which has low interference between partitions, for example. So you can use this in different ways, and it's transparent, the software. I mean, you set this up, but then the software doesn't really know what's happening here. So integrated peripherals, yeah. So of course there's a number of interfaces. I mean, we have some high-speed interfaces based on SerDes links. So Space Fiber, PCI Express Generation 3. So we have a total of 12 links, 4 Space Fiber ones and 8 PCI Express ones, and we allow some different, let's say, configurations there. We also have a bunch of, let's say, slower industry standard interfaces to talk to other boxes. And in addition to these I/O interfaces, we have a number of integrated functions on the chip. And the goal with that is to reduce the need for larger companion FPGAs. So, I mean, we're hoping that many problems can be solved with this device on its own. So, I mean, we have a NAND flash controller to store lots of data, and we have an embedded FPGA for glue logic, or maybe certain accelerators and so on. We have a time-triggered Ethernet switch, so we have 6 ports, gigabit ports out. We're integrating a GNSS receiver IP, and our SpaceWire router, which was also in the 740, with added SpaceWire to Space Fiber bridging, so you could make a basic kind of aggregator with the chip. And we also have our external FPGA scrubber. So we'll have the NanoExplorer 32K LUT eFPGA inside, and it's integrated in SoC. So you could add your own IP core and kind of integrate it, and it will act as if it was part of the ASIC. So you can do DMA access and so on. We have some features to improve security in the system compared to earlier. So one of the things we have done here is an authenticated boot scheme, where instead, as we have done on most of our previous products, we just start executing out of ROM. We have a state machine which pulls in a firmware image, authenticates it against a public key, which we have in one-time programmable storage, checks that it's okay before it starts CPU, so we can be sure that the code is okay before we run the first instruction. And this is done purely, completely in hardware. We also have additional isolated subsystem or hardware security module, which is like an SoC that lives its own life and which you can use to provide attestation, key generation and such. It has some specialized cores for crypto acceleration and entropy, random key generation and so on. And this is optional because it requires an external SPI flash for its storage, but if you need it, it is there. We are working with a third-party provider as well to develop some software for this. We're bringing our software ecosystem to this. For Leon, everything is pretty much there. For the Noel side, it's coming. Most of this is in place. We're filling the gaps as we go along. And the TSIM3 here was just recently released in the GR765 version, first targeting the Spark side and aiming to provide the RISC-V counterpart in a short time, later this year, I believe. Conclusions, it builds on our earlier GR740 device, and yeah, we put an emphasis on performance, power efficiency, with a high degree of integration, and we have a strong software ecosystem to support it. That was it, and I think my time was up, so thank you for listening.